This video is a summary of the C3 Quantitative Chemistry for AQA Trilogy Foundation tier. During this video we will look at the topic question, how is mass conserved and how can reaction masses be calculated? Looking at picture A then, 5 grams plus 5 grams would give us a total of 10 grams. On picture B, 1 gram plus 8 grams gives us a total of 9 grams. On picture C, what number would we need to add to 5 to get to 8 grams? That would be 3 grams. And then finally, what number would we need to add to 9 to get to 20 grams? That would be 11 grams. And what each of these pictures illustrates is the total sum on the left hand side is equal to the sum on the right hand side. The pictures we've just seen are important because we can apply this to chemistry, where the total mass of the reactants is equal to the total mass of the products in any reaction. This means mass is not created or destroyed in the reaction, and we call this the law of conservation of mass. This can be employed then in examination style questions. So here we see that with titanium chloride it reacts with sodium to produce titanium and sodium chloride. In the reaction it tells us that 1140 kilograms of titanium chloride completely react with 552 kilograms of sodium. This produced 1404 kilograms of sodium chloride, and the question then asks you to calculate the mass of titanium produced from this reaction. As you can see, this is a 1 mark question, so we're not looking for a complicated calculation with this. So in tackling questions of this nature, annotate the question with everything that you know. Check that your units are the same, highlight what's missing and rearrange to find your unknown quantity. So here I know that I've got 1140 kilograms, so I'm going to annotate my equation with that, and I can continue with the mass of sodium and the mass of sodium chloride. I now know, due to the conservation of mass, that the sum of both sides must be the same, and I'm calculating the mass of titanium. This gives me the equation shown, so 1140 plus 552 is equal to x, that's the one thing I'm trying to find out, plus 1440. So I can rearrange this equation to find x, and my final mass is 288 kilograms of titanium. Looking at the video that's showing on the right hand side, what can you observe? So that means what do you see, what do you think is happening, and what do you think the iron is reacting with? Well, the reaction that we're seeing is the reaction of iron and oxygen to form iron oxide. Oxygen from the air is reacting with the iron. And we can balance the equation to show that 4 atoms of iron react with 3 molecules of oxygen to form 2 molecules of iron oxide. Because we'd originally started with the iron, if we did this on a balance, it would appear that mass had increased because the oxygen is adding to the iron, and when they combine you are adding 2 masses together. the mass would appear to increase because the product iron oxide contains all of the atoms from the iron and the oxygen. So we would need to add the masses of the iron atoms and the oxygen atoms together. And this would show us then that mass had been conserved. So here we have a different reaction, and in this reaction, were we to do it on a balance, it would appear that mass had been lost. Why do you think that might be? Well, in this case, hydrogen gas is produced. So if the gas was able to leave the reaction, i.e. if it didn't have a lid on it, then that mass of hydrogen would appear to have been lost. Let's look in a little bit more detail at masses then. So first of all, we're going to look at relative formula mass. So first of all, let's remind ourselves about chemical formula. The formula will show us the type and the number of atoms that are bonded together to form a molecule. So in our molecule of methane, you can see that there is a carbon in the middle and there are 4 hydrogens bonded to that carbon. And if we were to write the formula of that, we would write that as CH4. We've got 1 carbon and the 4 appears directly after the hydrogen to show us we have 4 atoms of hydrogen. We can do that then for carbon dioxide, something you're quite familiar with. That's 1 carbon and 2 oxygen. And finally for water. It's really important that we use subscripts for writing these formulae. If we don't, you will lose easy marks. So when we calculate the formula mass of a compound, what we do is we add up the masses of each of the individual atoms in the molecule. So here we have ammonia and its formula is NH3. We've just seen that that tells us it's got 1 nitrogen and 3 hydrogens. So if we were to work out the formula mass of ammonia, then we need to add 14, which is the mass of nitrogen, plus 3 times 1, because 1 is the mass of hydrogen and we have 3 of them. If we add that all together, we get a formula mass of 17. We can do the same for sodium oxide. So in this case we have 2 sodium atoms, so that's 2 times 23, and we have 1 oxygen, which is 16. So we add 2 times 23 plus 16, we get an answer of 62. So they're quite straightforward. But then we have formula with brackets in. So in this case, the first thing you do is work out what's inside the brackets and then times it by the number outside of the brackets. So using this example, we've got 24, which represents the mass of magnesium, and then this small 2 outside of the brackets now comes in front of it, and inside of the brackets we would have 16 plus 1, 16 being the mass of oxygen, 1 being the mass of hydrogen. We add all that together, we get 58. We do the same for calcium nitrate then. This one's a little bit more complicated. 40 would be the mass of calcium, and then we have inside of the brackets, we have 14 for the nitrogen, and we have 3 times 16 because there's a 3 directly after the oxygen, but then all of that added together needs to be times by 2 because there is a 2 outside of the brackets. Sometimes we might want to know what percentage of a compound is made up of a particular element, and this is called the percentage composition by mass. Because it's a percentage, we are going to be multiplying our fraction by 100. So the number of atoms of whatever element it is that we're trying to find out times the atomic mass of that element, and then divide by the formula mass of the compound. So let's have a look at a worked example. Here we're going to calculate the percentage of oxygen in carbon dioxide. So the formula for carbon dioxide is CO2. This tells us that we have 2 oxygen atoms because the 2 is directly after the O. Each oxygen atom has a mass of 16. And the total formula mass for carbon dioxide will be 12 plus 2 times 16, which gives us 44. That's all the information I need to know to work out the percentage of oxygen in carbon dioxide. Let's do the calculation then. So I have 2 atoms of oxygen times the atomic mass of oxygen, which is 16, divided by the formula mass of the compound, which is 44, and then to turn it into a percentage I multiply that by 100, and that gives me 72.7%. Let's now look at concentration. This topic is appropriate for both higher and foundation tier students. What does concentration actually mean? Do we know how many centimetres there are in a metre, and therefore how many centimetres cubed would there be in a metre cubed? Well, concentration is the number of particles per unit volume. In a metre there are 100 centimetres. So if we're working out centimetres cubed in a metre cubed, to work out a volume we multiply each of the sides. So it would be 100 times 100 times 100, which is 1,000,000 centimetres cubed in a metre cubed. So thinking specifically about particles then, here I have a picture of a concentrated acid. It's got lots of acid particles dissolved in it. If I compare this to a dilute acid, you can see there are only a small number of particles dissolved in this acid, so this would be dilute. So what is a decimetre? Well, deci usually means 1/10, and if we had a decimetre, 1/10 of a metre or 0.1 metre is 10 centimetres. But if we wanted a decimetre cubed, then the number of centimetres cubed in a decimetre cubed is 10 times 10 times 10, or in other words 1,000 centimetres cubed. Now you may see this written as 1 litre, but litres are not SI units, they're not standard units, and therefore we don't use them. We have to talk about decimetres cubed rather than litres. The units for concentration are moles per decimetre cubed. So what do you think the equation for calculating concentration is? Well, if moles per decimetre cubed is our units, that means we've got moles divided by decimetres cubed. So if we turn this into an equation, concentration is equal to moles divided by volume. This is an equation that will not be given to you in the exam, so it's worth remembering. The concentration of solution is measured in moles per cubic decimetre, or moles per decimetre cubed. So for example, if I had 8 moles dissolved in 4 decimetres cubed, the concentration would be 8 divided by 4, or in other words 2 moles per decimetre cubed. Concentration can also be measured in grams per cubic decimetre or decimetre cubed, and that's the number of grams in 1 decimetre cubed. Now remembering that mass equals mR times moles, we can convert concentration in moles per decimetre cubed to grams per decimetre cubed by multiplying by the formula mass. So to summarise, concentration is moles divided by volume. If we convert centimetres cubed to decimetres cubed, we divide by 1,000. And to work out the concentration in grams per decimetre cubed, we take the concentration in moles per decimetre cubed and multiply that by the formula mass.